It's pretty clear where you would use machine learning models such as classification and regression. What are some of the real world use cases for unsupervised learning algorithms? The kind of machine learning problems that we've tackled so far in TensorFlow have been largely supervised algorithms. Supervised algorithms have a distinct training phase where you input training data with the corresponding labels. And the algorithm uses the data and the labels in order to tweak its machine learning parameters. Unsupervised learning, however, has no labeled data and no distinct training phase. Algorithms such as regression and classification are canonical supervised learning problems. If you have a function y is equal to f of x, where the function f connects the inputs with the outputs, the algorithm will try to learn this function, will try to reverse engineer this function. The data that you feed to unsupervised learning algorithms have no y values corresponding to the x input. So there is no function connecting the input to the output that it attempts to learn. Instead, it just looks at the x data and tries to find interesting patterns within it. Two common applications of unsupervised learning are clustering and principal components analysis. Clustering seeks to find logical groupings within data so that data which is similar to each other is grouped together in a single cluster, and data that is different is present in different cluster. Principal components analysis is useful for dimensionality reduction, where we attempt to express data using the fewest possible dimensions, that is, the principal components of the data. We'll start off by understanding the differences between supervised and unsupervised learning. Let's take the classic example of supervised learning that we've been working with so far, the ML based classifier. We feed a huge corpus of data into this classifier during the training phase. It outputs a classification, and we check whether the predicted label is equal to the actual label, and the difference between this we feed back as a cost function to tweak our machine learning model parameters. This feedback is essential to improve our model parameters so that we can use this model for prediction. This cost function calculates the difference between the predicted value that was output by our ML model and the actual value associated with the input instance, which means every instance that we feed in into this model during the training phase has to have an actual value associated with it. This is the label. And really, a lot of the stuff that we've spoken of so far, such as the training process, the loss function, gradient descent optimization, backpropagation to train a neural network, all of this really applies to supervised learning. Supervised learning refers to all machine learning algorithms where labels are associated with the training data, and these labels are used to correct the algorithm and tweak the model parameters. Unsupervised learning algorithms, on the other hand, have no labels which can be used to train or correct or supervise the data. Here, your machine learning model has to be set up just right so that it can learn the structure which exists within the data. It can find patterns within the data without having any external correction mechanism. Here are some of the characteristics of supervised learning. That's all we've studied so far, so you should be intimately familiar with it. We have the input variable x, that is the features, and the output variable y, which are the labels for our data. We know that there is some function f which connects the input data, that is the x, to the y. This function f of x is what supervised learning tries to reverse engineer and figure out. It tries to approximate this mapping function so that when we input new values of x, we can then predict the value of y. Supervised learning generally starts off with some approximation of the mapping function and then uses the training dataset, which has the y labels, to correct and tweak the mapping function approximation. Let's compare these to the characteristics of unsupervised learning algorithms. The data that you feed into an unsupervised learning model has only the x values. There are no corresponding y labels. There is nothing that you can use to correct and tweak the model parameters. Unsupervised learning algorithms try to seek information within the data itself. It tries to model the underlying structure to learn more about the dataset to find patterns within it. These algorithms can be thought of as self discovering algorithms. They find the patterns and structure in the data by themselves. using only the native characteristics of the data and no external information. It's fairly easy to spot unsupervised learning algorithms. Look for machine learning models which do not have Y variables for their training data and do not have a labeled corpus. Because unsupervised learning algorithms are inward focused, that is, they focus on the data themselves and not on external labels, you can think of unsupervised learning as a kind of introspection. Why would you look within? Let's see why you would do so in life and in machine learning. You would look inward in your life if you wanted to be emotionally self sufficient. In the case of machine learning, you want the unlabeled data to be self sufficient. If you look at the data that is available in this world today, a very small fraction of it is labeled, which is why a very small fraction of it is what we can use for supervised learning models. Unsupervised learning algorithms allows you to build a huge amount of data into play, data that is unlabeled. In life, you might introspect or look within to learn what values matter to you. Similarly, in machine learning, latent factor analysis or finding the hidden factors or patterns in data is a reason to look within. In life, introspection helps you identify other people who share your values. These are important, these are your friends. Similarly, in machine learning, this is what clustering does, identifies data that share the same characteristics. Looking within also helps you identify those people who don't share your values. You know you have to stay away from them. And that is exactly anomaly detection. Unsupervised learning techniques allow you to detect those bits of data which don't fit into your pattern, which are outliers or anomalies. Looking within allows you to identify and eliminate those things in your life that do not matter, and that is quantization. Quantization is the process of converting a continuous range of values into a finite range of discrete values or buckets. Unsupervised learning techniques help with quantization. And finally, an important reason for you to look within yourself in life is to train yourself to navigate the outside world. Similarly, in the world of unsupervised learning, these techniques serve as pre training for supervised learning problems such as classification and regression. So, you'll pre train your model on a huge data set which is unlabeled and then use the training data set that is labeled for classification or regression. Let's look at a use case for each of these unsupervised learning ML techniques that we just described. Making unlabeled data self sufficient allows us to identify photos of a specific individual. Let's say there are thousands of photographs of you, but none of them are tagged with your name. Unsupervised learning algorithms will be able to figure out that all of these are the same individual, and if you tag one of these, all the rest will be tagged as well. Latent factor analysis is often used in stock market prediction algorithms. If you want to find the common factors which drive the values of 200 stocks, latent factor analysis is what you'd use, the hidden patterns which affect stock movements. Clustering can be used to find relevant documents from a huge corpus. Let's say you're doing legal discovery and you want to find all the emails that relate to a particular topic. Clustering is an algorithm that you might choose to use. Anomaly detection techniques, which are also unsupervised learning models, have a wide range of applications. One of the most common is to flag fraudulent credit card transactions. If a transaction occurred on your credit card and it doesn't fit the pattern that you normally follow, that is an anomaly that can be detected using an unsupervised model. Quantization is used to map a large range of continuous values into a smaller, more discrete range. So, if you want to compress true color, which is 24-bit, into an 8-bit representation, quantization will help you there. And really, unsupervised learning techniques can be used as pre training for supervised learning problems for all of these use cases. Image recognition, latent factor analysis, classification problems of all kinds, anomaly detection, all of these models can be pre trained using unsupervised learning techniques. And here are the unsupervised learning algorithms which help with all of these use cases. Autoencoders are used to make unlabeled data self sufficient in latent factor analysis, in anomaly detection. Clustering is used for quantization, and really for Pre training for supervised learning models, we use all of these techniques. In this section, we're going to focus on two specific unsupervised learning techniques. The first will be clustering, where we identify patterns in data using K means clustering. The second is autoencoding, where we identify latent factors that drive data. In fact, principal components analysis can be performed using autoencoders. Two common unsupervised learning techniques which are widely used are clustering and autoencoders. Clustering can be used to find logical groups in the underlying data. Let's say you're doing legal discovery and you want to find all emails sent within a corporation which pertain to a certain topic. Clustering is the algorithm that you would use. Or if you want to find Facebook users who like the same music so that you can target ads to them, that is a clustering use case as well. Autoencoders are used for dimensionality reduction and to find the latent factors in underlying data. If you want to find the common drivers of 200 separate stocks, you would use autoencoders. Or if you want to find the fraudulent credit card transaction amongst many other real transactions, you would use autoencoders. Both clustering and autoencoders can be used for pre training, a preparatory step for machine learning models using supervised learning, such as classification or regression.